Okay, so here's the analysis part of the lab, which is a little easier than some of the other ones we've been doing. So the acceleration of that we measured today is equal to the mass, hanging mass times the acceleration due to gravity, which is the weight. So that's our force, and then we divide by the inertia of the system. So we have the moment of inertia of the disk divided by the radius of the pulley squared. So that's the inertia, the equivalent linear inertia of the disk. And then we have the two masses, the mass of the cart and the mass of the hanging mass. So that's our theoretical calculation. For the second part, this moment of inertia term will be 0. So let's go ahead and put down the constants that we have. So let's do mass of the cart. And let's go ahead and put all these in the units that are appropriate. So the mass of the cart is 0.4, for me, 0.4943 kilograms. The radius of the pulley, so I'm going to go ahead and calculate that. It's equal to the diameter, which is 4.774 centimeters. So we're going to divide that by 2 to get the radius, and divide by 100 to get meters. So that is the radius of the pulley in meters. We have the radius of the disk. We actually won't need this because we already calculated the moment of inertia, but I'm going to go ahead and put it in here anyway. So the radius is 9.6 centimeters divided by 2 to get into radius, divided by 100. So that's the radius of the disk. I'm going to go ahead and just make these wider by clicking between the columns so we can see everything. Okay, let's go down here. Let's do the mass of the disk. Again, we don't need this, but we're going to put it anyway. 0.185 kilograms. And then what else do we need? We need the moment of inertia. So we have actually already calculated this, but let's just double check. So it's equal to 0.5 times the mass of the disk, which is this cell B2, times the radius of the disk squared. And I should get what I have written on the paper, which I have 1.36 times 10 to the minus 4. So that is good. And units are kilograms, meters squared. And let me double click between two columns to get those in the right width. Okay, so that's all the stuff we need. Now, this column will be hanging mass. So I'm going to put it in grams. I'll have to convert it later. So let's actually put the units in. So what I'm going to do is I'm going to highlight this, and I'm going to do Control X, and then move one cell down and do Control V. Okay, so these are grams. So the hanging mass 25, 45, 65, 85, 105. And then we have the accelerations, and those units are meters per second. Go here to font, choose superscript, and then square it. And again, let's double click between C and C so we can see the entire thing. So we got the hanging mass in grams, get the acceleration. These are the measured ones. And I'll put calc, Excel, and what I'll do is I'll just copy these units over. So to copy something, you just highlight the cell, hit corner, just do like that, except it made it seconds cubed, so that's not going to work. So do Control C, and then Control V, and that'll work. Okay. So that's the calculated acceleration, the measured and the calculated. So the measured's from my data sheet, so you put your data in there. And we're going to do the one with the disk first. So let's go ahead and put this some identifier here with disk. Okay, so the calculation. So we just looked at it a second ago. So here's the equation, equals M2, which is the hanging mass, but that's in grams, so I'm going to divide that by 1,000. Actually, let's go back. Left parenthesis. So we need to make sure this is all in the numerator. So we're going to have the hanging mass divided by 1,000 to get into kilograms times G, 9.81. Okay, so that's the numerator. And then we divide by the moment of inertia. Now we don't want that to increment, so we're going to push F4. We're going to divide that by the radius of the pulley. Push F4 and then square it. So that's I divided by radius of the pulley squared plus M1, which is the mass of the cart. So that's B1. Push F4 and then add the mass of the hanging mass, which is this one. That's M2. We've got to divide by 1,000. And we want, and then a right parenthesis, so that should be right. So we got M2 times G divided by I divided by R, the pulley squared, plus M1 with mass of the cart, which doesn't change, plus the hanging mass, which is going to change, divided by 1,000 to get everything in the right units. Hopefully, when we push enter, we'll get some number that's probably slightly greater than what we measured. That's a lot greater than we measured. So why is that? So I'm going to pause for just a second. Okay, so I checked it, and I don't see any issues. So we're going to go through the whole thing, and then I'll explain why I think this is okay. So that is the calculated accelerations, and our actual accelerations are quite a bit less. And then we'll do the accelerations for the second part. So this is without disk. So we got the hanging mass in grams. We've already got that, so we don't need to do it again. Well, let's go ahead and do it. So we can actually use we can copy things. So then we have the measured acceleration, and let's copy the units. And then we'll do the calc acceleration. Copy the units again. Okay. So let's put in the values: 0.424, 0.764, 0.28, 1.38.65. So those are without the disk. Now the calculation will be the same. So I'm just going to copy this equation over here, except I'm going to get rid of the moment of inertia term. So I'm going to go up to the equation. I'm just going to use backspace to get rid of that first term in the denominator. So it's now just the mass of the cart plus the hanging mass. And I put that, and I get 0.47 something. And then I'm going to copy that equation down. Now let's change all these decimals to two decimal points. I'm going to highlight these, right-click, format, number 2. Okay. So it's format number 2. So you can see there, 2 decimal points. I'm going to do the same thing over here. So highlight them, right-click, format, number, 2 decimal places. Okay. Now you can see that the agreement is much better here. You would expect the measured to be less than the calculated because you've got friction and you've also got moment of inertia of the moment of inertia of the actual rotary motion sensor. So it's not surprising they're lower. They're pretty consistently lower by about 0.06. So the question is, why do these agree so well and these don't agree? Well, here's my hypothesis. The hypothesis is that I'm getting slippage of the thread, and so the thread is actually not moving as quickly as the actual calculated value. And I think that's the right assumption. If I come up with a better explanation, I'll let you know. But right now I don't see anything that is causing this to change my mind, because I looked at the moment of inertia of the disk, and it seems to be the value would expect this amount of change. So unless I'm calculating the moment of inertia of the disk incorrectly, then it should be okay. And you can see it's 1/2 the mass of the disk times the radius of the disk squared. I can't see how I can do that any different. And the only way I could do that is somehow increasing the moment of inertia of the object. And I don't see how I can do that. I could go in here and take the moment of inertia and multiply it by 2 or something like that. And you can see how that brings these numbers down considerably. So in the absence of figuring out what's causing the moment of inertia not to be low, I have to come up with some other explanation, which I am attributing to the fact that we're getting slippage. We'll go ahead and plot these 2 graphs. I mean, you can see it visually here, but what we could do is we could highlight this first set and go to Insert, Chart. Let's go ahead and put lines between them. Let's use the second one here. Okay, so there we go. Let's move this to another tab. So right-click, move chart, new sheet. We'll call this with disk. Say OK. And let's get some names on here. So one will be theoretical, one will be actual. So we're going to select data. We'll edit, and we'll call series series 1. Yeah, this would be actual acceleration. Say OK. Pick the second series, edit that one, call that the calculated acceleration. That way the legend is correct. And we'll put a chart title up here. So let's go click on chart title, say comparison of actual and theoretical acceleration with disk. Okay. We need axis titles, so I think if we click on the graph, go to this plus sign, click you want axis titles. So the x-axis title is hanging mass in grams, and the vertical axis title is going to be acceleration meters per second Get rid of that extra bit. Okay, so we've got acceleration, got hanging mass in grams, title, got a legend. Let's move the legend. Let's click on the legend, right click, format legend, and move that to the top. Kind of like the top instead of the bottom. Okay, close that. Okay, so that's with the disk. And probably the easiest thing to do, instead of making the graph all over, what we'll do is we'll right click here, we'll say move or copy, create a copy. And what we'll do now is we will go and change the data. So let's click on the graph, go to design, choose select data. And you can see here it's A7 through C right there. It's this one. So all we have to do is click on the corner here and then highlight this set of data. Push enter. It should still have the titles. So there you can see how much better they agree. No, they don't have the titles here, so we need to go back to the data. Series 1 is the actual. Series 2 is the theoretical. So we'll go to edit. We'll say actual acceleration. Okay. Go to series 2. Edit here. Theoretical acceleration. Okay. So let's compare the two graphs now. Actual acceleration, calculated acceleration, hanging mass. Okay. So the only thing we need to do is we need to change the title. So we'll click on the title and we'll say without disk. So let's go to the title here down on the tab. So let's say without disk. The sheet 1, we'll right click on that and rename as data. So we got the data, we've got with the disk, we've got without the disk, and we could, change the font size, but let's just leave it as it is. So it's interesting. And that's it.